Have you ever wondered why we can't just press an enhance button and turn any old video into crystal clear 4K? Well, it's because for an AI, that is a ridiculously hard problem. It takes a staggering amount of computing power. But what if there was a completely different way to do it? A faster, smarter way? Today, we're going to break down a new model that might just be the answer we've been looking for.
All right, here's the game plan. First up, we'll get into why high-res video is such a tough nut to crack. Then, we'll see why the old AI models kind of fell short and meet a new contender called Mamba. After that, we'll uncover the clever gather-scatter trick that really unlocks its potential, look at the pretty impressive results, and finally, we'll talk about why this breakthrough is such a big deal.
So let's dive right in. What is it about video that's so incredibly difficult for AI? To really get why this new solution is so special, we first have to understand the core problem it was designed to solve.
I mean, think about it. Upgrading a single photo, that's just one moment in time, a snapshot. But a full movie, you're talking about tens, maybe hundreds of thousands of frames. It's this constantly moving, constantly changing river of data. The sheer amount of information is one thing, but the real challenge is consistency. Making sure that what happens in frame 1 still makes sense by the time you get to frame 10,000.
This whole process actually has a name: Video Super Resolution, or VSR for short. And the key phrase here is leveraging details from neighboring frames. See, an AI can't just treat every frame like a separate photograph. If it did, you'd get this awful, flickering, inconsistent mess. It has to be smart. It has to look forwards and backwards in time to intelligently guess what details are missing. Okay, so let's look at the old guard, the two former champions of AI. On one hand, you had RNNs. They go through a video frame by frame, which sounds logical, but they have a terrible long-term memory. They basically forget what happened a few seconds ago. Then you have transformers. They're amazing because they see the whole picture at once, but that comes at a cost, a huge cost. It's called quadratic complexity, which is a fancy way of saying their processing cost just explodes. If you double the length of the video, you don't just double the work, you quadruple it or more. For high-res video, that's a total deal breaker.
So yeah, it's pretty clear the old ways just weren't built for the marathon that is high-resolution video. And this is where our new contender, Mamba, steps into the ring with a completely different approach.
Now, Mamba isn't just a random name. It's part of a whole family of models called state space models, or SSMs. These things have their roots in engineering, and they were basically purpose-built for one thing: handling incredibly long sequences of data super efficiently. And Mamba? It's the newest, most advanced version, really optimized for the kind of scale we see in modern AI. And here it is. This is Mamba's secret weapon: linear time complexity. Instead of the transformer's explosive, quadratic cost, Mamba scales linearly. That means if you double the video length, you just double the work. That's it. It's predictable, it's manageable, and that is what makes it a perfect candidate for handling video. But of course, there's always a catch, right? If Mamba is this blazing fast, why isn't it already in every video tool out there? Well, it turns out its greatest strength is also tied to its biggest weakness. It gets really, really confused by movement. So here's the thing. To process a frame, Mamba basically flattens it into one long single line of pixels. And as the paper points out, even a tiny bit of movement between frames creates these massive positional distortions. Just imagine a car moves a little to the right. A pixel that was right next to another one might suddenly be thousands of spots down the line in that flattened out sequence. For Mamba, it's just pure chaos. It can't make sense of it. And this is where the real genius of this research comes into play. The scientists realized they didn't need to change Mamba, they just needed to change the data that Mamba sees, and that is the gather-scatter solution. The whole process is actually beautifully simple. First, it just grabs a small group of frames. Then comes the gather step, and this is crucial. It uses motion tracking to warp and align every single frame in that group so they all line up perfectly with a frame in the middle, called the anchor. Now that everything's perfectly still, it lets the superfast Mamba do its thing. And finally, the scatter step. It takes all those improvements and intelligently spreads them back out to all the original, messy, unlined frames. But the secret sauce is how it aligns them. You see, older methods would only look backward, aligning past frames to the current one, but this new center-anchored way is much smarter. It looks both backward and forward in time. By using context from both directions, it gets a much cleaner, more accurate picture. This really helps cut down on those weird visual glitches when, say, a car drives behind a tree and comes out the other side. And here is the final brilliant piece of the efficiency puzzle. That's scatter phase. Absolutely no work is wasted. Instead of just enhancing one frame and throwing away the calculations for all the others, the model takes those improvements and distributes them back to all of the original frames in the window. It's the definition of work smarter, not harder, and it's baked right into the system.
Okay, so the theory sounds really elegant, but does it actually deliver? Let's check out the performance data and see how this thing really stacks up against the competition.
Honestly, this table really says it all. If you look at the column on the far right, PSNR, that's basically a score for image quality. Higher is better. And you can see GS Samba is right up there with the very best models. But now, look at the middle column, flops. That's the amount of work the computer has to do, so lower is better. It's getting pretty much the same top-tier quality while doing almost 40% less work. That is a massive, massive win.
And if that table wasn't clear enough, this bar chart just makes it painfully obvious. That much shorter bar for GS Mamba isn't just a tiny improvement. It's a fundamental leap in efficiency. It means faster processing, it means lower energy bills, and it opens up the door to running this kind of tech on way less powerful hardware.
And, it isn't just about the numbers on a chart. The researchers themselves say it flat out. The final video just looks better. It gives you sharper textures and fewer of those weird, distracting visual glitches that can sometimes ruin AI-enhanced video. At the end of the day, that's the real test, right? Superior perceptual quality. So what we have here is a model that's faster, cheaper to run, and produces better-looking video. Let's just zoom out for a second and think about what a breakthrough like this actually means for the future of AI and video. Let's just quickly recap the whole story, right? The big problem was that the old models were just too slow and expensive for long videos. Then this new tool, Mamba, came along. It was super fast, but it got confused by any kind of motion. The solution was the brilliant gather-scatter trick, which neatly pre-aligns the frames for Mamba. And the impact? State-of-the-art results with a huge boost in efficiency.
So the big takeaway here is really simple. Gather-Scatter Mamba isn't just a one-off clever trick. It's proof. It's a signal that this entire family of models, these state-space models, could very well be the future of video processing. They offer a path to incredible performance without the absolutely crushing computational costs we're used to.
And that kind of leaves us with one last big thought to chew on. The exact same efficiency that makes it possible to restore and enhance video from the past could soon be applied to creating and changing video right now, in the present. So if we can now fix the past this efficiently, what are we going to be able to create in real time tomorrow?